Hey everybody, this is Mrs. Bernacki. Hopefully you are all doing well during this crazy time. I decided that for today I would teach you myself, record a video and post it for you to watch, and take a break from some of those Khan Academy videos and other YouTube videos. So I hope you enjoy. For those who did not get a chance to watch my homework review video that I posted over the weekend, please try and take a moment at some point to look over that. I went through some of the homework problems from last week in case you were having any questions. But also in there I mentioned that my stylus for my iPad decided to die recently. Perfect timing, of course. And so I'm writing everything on this iPad with my fingertips. So some of my writing will be a little messy. I apologize. I'm going to do my best so that it's all legible. But anyway, so today we are starting to talk about something called the antiderivative. Now, up until this point, we've been doing everything based on the derivative of a function, right? We start out with some sort of f of x value. We take the derivative of that value, and then we end up with some sort of f prime of x. Well, now the antiderivative is now we're going to be going backwards. So we're going to be starting with some sort of f prime of x function, and we want to go backwards to see what was the original function that we would have started with. All right, so that is something called the antiderivative. That is what is going to be the process for allowing us to find the actual area under the curve. So last week we, created all these rectangles using our Riemann sum in order to estimate the area under the curve. But as we talked about, then you're left with all this excess space that doesn't get counted towards that area. So that's why it was just an approximation for a Riemann sum rather than an actual area. So what the antiderivative is going to do for us is, let's say that I want to find the area on the interval from 0 to 6, which is an interval that we dealt with some of those problems. Well, now I'm going to be able to find the exact area. There's not going to be any gaps left over. There's not going to be any excess space. And obviously I can't just fill this, but hopefully you get the idea. We're going to be able to find that entire area, the exact value, and we're going to be using calculus to do that, using this process of the antiderivative. Now, when we talk about the antiderivative, there are actually two different forms of the antiderivative. There's the indefinite integral and the definite integral. And just as a side note, please make sure you're taking notes during these videos. I know you can always go back and rewatch them at a later time, but it's definitely more beneficial, especially if you're doing homework or practice problems, to have some notes down that you can just quickly refer back to. But anyway, so this word integral, we often think about that. When we see the word integral, we think of our antiderivative process. Now, the integral is really a symbol. And it's a symbol that represents that we are dealing with an antiderivative. So that symbol kind of looks like this. It's almost like I'll call it a lazy S. It's kind of like you took an S and just, squished it on either side to make it a little taller and longer, but, you didn't flatten it completely to a straight line, but you squished it a little bit. All right, so anytime we see that symbol, that's going to represent that we're taking the antiderivative. Instead of seeing things like dy dx, dA dt, d dx, f prime of x, y prime, right? Those were all different types of things that we would look at and say, oh, well, to me, that means that we're dealing with the derivative, right? Anytime I saw any of these things. But now if I see this integral symbol, that means that we're going to be going in the opposite direction, dealing with the antiderivative. So let's go back to these definitions for a second. The indefinite integral, that's what we're going to talk about today. This is the process of antidifferentiation. So this is simply just finding the original function value. Okay, so you know how when we first started with derivatives, we spent quite a few days just finding the derivative of all the different types of functions, right? We had to take the derivative of a polynomial, but then we had to learn about the derivative of a natural log function, the derivative of a trig function, the derivative of an exponential function. We had to learn about the derivative using that U substitution. Okay, all these different processes. Well, that's what the indefinite integral represents, just simply finding the function. That's it. The definite integral is where you're going to actually find the exact area under the curve. Okay, so what I relate this to in the derivative world, if I said find the slope at x equals 2. Right? So f prime of 2. So this means that we first have to find the derivative function, and then you plug in at a certain x value. Right? So then we're finding the slope at a certain x value, so it's specific just to x equals 2. Okay? It's not the function anymore that's going to tell us any value. We just end up with one value at x equals 2. Well, that's what the definite integral does for us in the antiderivative process. We would find the exact area over the interval that we're looking at. Okay, so let's start with some basic integrals, antiderivatives. Well, the first one, the most basic one, is I'm going to kind of go backwards here. So if I take the derivative of x, right? What's the derivative of x? Hopefully you all said 1. All right? So that means that now I want to go backwards. So if I took the antiderivative of 1 and we put a little dx next to it. So anytime you're going to be taking the antiderivative, you're going to have your integral symbol, you're going to have the function that you're taking the antiderivative of, and then you're going to have a dx. That's pretty much telling us that my original function was based in x. Okay, so sometimes this value might be dt, and then my original function was based in t, like if we had a particle motion, position, velocity, acceleration, all that is with respect to t, so then this would have said dt. But for the most part, we're just going to be having dx's. Okay, well, if I am going backwards, right, if the derivative of x was 1, that means that if I started with 1 as my derivative and wanted to go backwards, my original function where I came from was x. But now we also have to put this funny little plus c afterwards. Now that c is going to represent some constant. And you might be asking, why in the world do I have to do that? Because my original problem here was just x. There was no constant after it, right? I took the derivative of x, and I got 1. So going from 1 back to the original, I should just get x. Why do I need this plus c? Well, you need that plus c because let's do the derivative of a few other things. If I took the derivative of x plus 2, well, the derivative of x is 1, the derivative of 2 is 0, so I end up with just 1. What's the derivative of x plus 10? Well, the derivative of x is 1, the derivative of 10 is 0. What's the derivative of x minus 4? Derivative of x is 1, derivative of negative 4 is 0. So I get all of these different variations where I always get the derivative equal to 1. So it's not just if I have x by itself, it's I could have x plus some constant, x plus some constant, x plus some constant, or minus some constant, right? All of those derivatives are the same value of 1. So when I'm going backwards for the antiderivative, I have to say, well, yeah, even though it's probably going to be x, it could be x plus one of those other constants, because I know the derivative of that constant would end up being a plus 0, and that plus 0 doesn't make a difference. I'd still end up just at 1. Okay, so again, I know this is kind of a weird concept to, transition into. Hopefully we are okay with that. Now, this doesn't happen just with 1. This happens with any variable. So if I take the antiderivative of 3, well, that is going to end up being 3x plus c. Why? Because the derivative of 3x plus c, derivative of 3x is 3, and the derivative of some constant would be 0, so that gives me a value of 3, the function that I originally started with. Okay, and this is the same pattern. So pretty much the antiderivative of any constant, which I'm going to just write k, antiderivative of any constant is going to be that constant times x, and then plus c for that extra constant that we could have. So if I were to quickly just write out, oops, not the derivative, if I were to write out antiderivative of 5 dx, antiderivative of negative 6 dx, and the antiderivative of, let's say, how about this one? All right, so antiderivative of 5 dx. Well, again, this 5 is a constant. So where did I have to start before that? It had to be 5x in order for when I took the derivative of 5x to end up with just 5. But again, in this process, any indefinite integral that you do is going to have a plus c. So the antiderivative of negative 6 dx is negative 6x plus c. And the antiderivative of pi, well, some people look at pi and be like, what do I do with that? Well, pi is just a constant, 3.1415926, on and on and on and on and on and on and on. It's just a constant. So we treat pi the same way we treat the 5, the negative 6, the 1, the 3, same thing. So this would be pi x plus c. Those are the answers to every single one of those questions. Okay? Now we're going to move on to taking the antiderivative of a polynomial. So I could take the antiderivative of more than one term. Now, what this is really asking us to do is to take the antiderivative of 1. Oh, that was a awful looking d. Plus the antiderivative of x dx. Right? So when we're taking the antiderivative of a polynomial, you're really taking the antiderivative of each term individually. Just like when we did the derivative, right? If we took the derivative of x squared plus 2x, we look at the derivative of x squared plus the derivative of 2x, right? You take the derivative of each term separately, so that means we take the antiderivative of each term separately. Now, it is not necessary at all for you to write this out, okay? I never do. Most people do not, okay? But I just wanted to give you a sense of what exactly we were doing. Well, okay, so if we were to take the antiderivative of 1, right? Well, we did that already. We get just x. Now, the antiderivative of x. Okay, so this one's going to be another rule. I'm going to write it over here. Antiderivative of x dx. Well, in order to get x after I take the derivative, that means that I had to have started with x squared. But if I take the derivative of x squared, I end up with 2x. I don't have a 2 over here. So that means that it had to have been divided out. So I would have had to divide by a 2 also in order to get to that x. So this means that pretty much our rule for the antiderivative of any x value, x to any power, is you are going to add 1 to the exponent, right? When we did the derivative, you always subtracted 1. So now we're going in the opposite direction, so we have to add 1 to the exponent. And what you then have to do is you're going to divide by whatever that exponent is. All right, and I know that seems like a little weird thing to have to do, but again, that is the reason why back up here, derivative of x squared is 2x, but I don't have the 2 here. Where did it go? Oh, because it got divided out. So we have to make up for that in our rule. So this is definitely a rule that you want to write down somewhere. Okay, antiderivative of x to any power n is going to become x to the n plus 1. You're going to add 1 to that exponent, and then you divide by the new exponent. So coming back over here to our original function, derivative of 1 was x, the antiderivative of 1 was x. The antiderivative of x is going to be x squared over 2. Because again, this was originally an exponent of 1. I have to add 1 to that exponent, and I have to divide by that new exponent. And then we have to put a plus c here. Again, any indefinite integral is going to need a plus c. Well, let's just double check our work. Let's make sure that we actually did that correctly. And now take the derivative of this function. Now I'm going to rewrite x squared over 2 a little differently, because there's really a 1 in front of that x squared, so I could really write that as 1/2 of x squared plus c. Right? So those two things are interchangeable. So if I look back at the derivative and I take the derivative of this whole thing, well, the derivative of x is 1 plus the derivative of 1/2 x squared. Well, 2 times 1/2 is 1, and x squared is going to become x to the first power. And the derivative of any constant is 0. So that leaves me with 1 plus x. Was that the original function I started with? Absolutely. So that means that we took the antiderivative appropriately and correctly. Moving on, so here are 2 more examples of antiderivative of polynomials. So again, we just take the antiderivative of each piece individually. So when we take the derivative, the constant always stays. Well, that's the same thing with the antiderivative. The constant always stays. So this 3 is just going to hang out here, and now I just have to deal with what was the antiderivative of x. Well, the rule that we talked about was the antiderivative of x to any power is going to be, we're going to add 1 to that exponent, and then we have to divide the whole thing by that new exponent. So if this original exponent was 1, well, I add 1 to that, so 1 plus 1 is going to become x squared, and I have to divide by that new exponent. So this is going to be 3x squared over 2. Plus, now I do the same thing for my x squared. Okay, I'm using this same rule here. So my original exponent is 2, add 1 to that, I get a new exponent of 3, and we have to divide by that exponent of 3. And we can't forget our plus c. And that right there is our answer. Okay, nothing else is needed. We are done with that problem. Moving on, polynomials, we know, could be large or small. We could have multiple terms or just 1 or 2 terms. This one we have a trinomial. Let's try it out. Okay, the antiderivative of 4. Well, going back to our first rule, antiderivative of any constant was that constant times x. So the antiderivative of 4 is going to be 4x, right? Because if we go backwards, the derivative of 4x would be just 4. That's the whole point here. Whatever I'm writing down here, it needs to be that the derivative of that would get me back to the original. So let me just erase this. Continuing on. Okay, so next term, minus, again, the constant, or coefficient I should say, stays. So the negative 2 is going to stay, and now we just deal with the antiderivative of x. which is back up here to our first rule. This is x to the first power, so it becomes x squared over 2, because I had to add 1 to that exponent and then divide by that new exponent. Plus 6 stays. Now we deal with the antiderivative of x squared. We'll add 1 to that exponent divided by that new exponent, and again, cannot forget about our plus c. Now, if you're writing out an answer, okay, and if it's a free response, it's fine to leave your answer like this. However, if you're doing examples on delta math or multiple choice questions, they're going to simplify this. So let's look at where we can simplify. Well, 4x is just 4x. But here I have 2x squared, right, 2x squared, divided by 2. Well, those 2's can cancel out, leaving me just with x squared. And over here I have 6x cubed divided by 3, so the 6 and the 3 can simplify to 2x cubed plus c. So this is really the best response, the most simplified response. And again, if we're doing practice on delta math or multiple choice questions, this one right here would be the answer choice. Okay, the best answer. All right, we're going to do one more today before we stop. And that one is just going to be trying out a little bit with our negative exponents. Now, we have dealt with this in the derivative format, okay? This is actually equivalent to if I asked for the antiderivative of 1 over x to the 4th plus 1 over x cubed dx, right? 1 over x to the 4th can be rewritten as x to the negative 4th power, and 1 over x cubed can be rewritten as x to the negative 3rd power. If you see the question in this form, you must rewrite it like this first. Same thing we did with our derivatives. We didn't take the derivative of 1 over x to the 4th and 1 over x cubed. We rewrote it as x to the negative 4th and x to the negative 3rd, so that we're only dealing with the power rule rather than some sort of quotient rule. All right, same thing. It's going to be easier for us to deal with this in this original format that I wrote. Okay. Now, even though we're dealing with negative exponents, I am still using this power rule for antiderivatives. Okay, we're going to add 1 to the exponent and then divide by that new exponent. So x to the negative 4th. Negative 4 plus 1 is going to become negative 3, and I'm going to divide by that negative 3, divide by that new exponent. Next one, plus x to the negative 3rd. Well, negative 3 plus 1 is negative 2. That's my new exponent. Divide by that new exponent. And again, add our plus c. Now again, just like the last problem, if this was a free response question, a short answer question, you could absolutely leave your answer in this format. However, delta math, multiple choice questions, they really don't like when your exponents are negative. So what will happen, again, especially with delta math practice, so I'm giving you the heads up now, is they will bring this term back down to the denominator so that it becomes a positive exponent. So if I bring that whole term down, that's going to leave me with a 1 in the numerator. The negative 3 is still in the denominator, and that x to the negative 3rd now becomes x cubed to the positive 3rd power in the denominator. Same thing over here. If I were to bring that x to the negative 2nd down, nothing is left in the numerator. Well, I shouldn't say nothing. A 1 is left in the numerator. Minus 2 and the x to the negative 2nd power becomes x to the positive 2nd power plus c. So this would be a good option. Okay. You may also, not to confuse you anymore, but you may also see where they may bring like the negative out in front, right? And like right here, if I'm adding a negative, this could just be subtraction. All right, so that's another option. I just want to show you different options on how that answer choice could be seen. Again, if you're giving multiple choice or delta math, if you're writing your answer with a negative exponent like up here and they say no, that's not correct, it's probably because they want one of these choices with the positive exponent. Okay? All right, well, that's it for today. I hope this was helpful. We're going to continue on with this tomorrow. And please let me know if you have any questions. Email me or, message me through Google Classroom if you have any questions. Okay? Hope you guys are all doing well, and hopefully we'll see each other soon. All right. Bye, guys.